Yeah, welcome to our podcast, appropriately named Stem Cells, the Podcasts.
So, I think we should start with some introductions. So, I'm Vilika.
I'm Garika.
And this is our podcast about everything STEM, basically.
Yeah, so it's really been a crazy year, right?
Yeah, so I believe one of our videos hit about 5k on YouTube.
Yeah, it was the egg drop video. That's honestly crazy because that was such a struggle to film. Do you remember that?
I think it took us about a good month.
It was really fun though. I enjoyed it.
Yeah. I mean, making the models was a struggle, but it was fun.
Yeah, it was. It was a struggle, but also it was so time consuming.
And we used a lot of tape.
We did, yeah. And yeah, we worked on that. So it's nice to see that for the amount of work we put in.
That is actually doing well.
Exactly.
So today we thought we'd talk about Millennial Prize problems, which I actually made a video on 2 weeks ago.
Yeah.
I mean, I think maybe a month ago, actually. I don't know.
It was at the start of December.
Yeah. So
yeah.
we did a little bit of an introduction on that, and we thought that, we couldn't fit everything about Millennial Prize problems into one YouTube video. So we thought, why not do it as our first episode on our podcast?
Yeah. Do you want to talk about where you kind of heard about these? Because they're not that common. I hadn't heard about them before you told me about them, and a lot of people don't know what they are. So do you want to talk about where you found out about them?
So the Millennial Prize problems are basically 7 well-known, not well-known, but they're very complex math problems, and they were selected by the Clay Mathematics Institute in 2000, and you get $1 million dollars for solving each one, which is an insane amount of money, if you ask me.
Yeah.
So
I mean, they're supposedly unsolvable, but one of them has been solved. So there's only 6 that haven't been solved. I say only, but there's still quite a lot.
So the one that has been solved is called the Poincare conjecture, and it basically states that a smooth finite shape with no holes in it in any dimension must be a sphere.
Yeah, so this one is it was solved by a Russian mathematician, Grigory Perelman, I believe.
Yes.
And that was in 2010. But I mean, can you believe it? He actually declined the award.
$1 million.
Yeah, because it wasn't offered to Richard Hamilton, and that was the person whose work he built upon. I mean, I respect the move, but it's $1 million. Come on.
I believe Richard Hamilton also rejected the $1 million for some reason.
Yeah. Like you were saying earlier, they're in it for the maths, not the money.
Yeah, not the money.
Fair enough, I respect it. But he actually proved the conjecture by deforming the manifold using the Ricci flow. Do you want to try and explain what that is?
So, the Ricci flow, gonna be honest, does not make 100% sense to us, but the internet says that the Ricci flow is something that behaves similarly to the heat equation, and describes the diffusion of heat through an object. So you must have heard of diffusion in biology, high concentration to low concentration, all of that. And yeah, that is as much sense as it makes to us.
Yeah. Funny thing about the Millennial Prize problems, I was actually telling you earlier that I think we should try and solve one of them. But
we did our research and thought maybe not.
Yeah, I can tell why the prize is $1 million.
No, it's definitely worth more than $1 million in my opinion.
Yeah, definitely. There's another one called the Yang-Mills and mass gap.
Yeah, so that one, the mass gap is basically the difference in energy between the vacuum and the next lowest energy state. So the one above it.
Yeah.
Do you want to go on about vacuum energy?
Yeah, so the energy of the vacuum it's defined as 0. So we're basically then assuming that all the energy states can kind of be thought of like particles in plane waves, and so therefore the mass gap is the mass of the lightest particle. So that's kind of what you're trying to prove. You're trying to prove that the mass of the least massive, so the lightest particle, is a positive mass. So do you want to talk a bit about the Yang-Mills theory then?
Yes, so the Yang-Mills theory is quantum physics, and it says that it's the generalization of Maxwell's work on electromagnetic forces to nuclear forces, and that is a key part of the standard model of particle physics. And the standard model is said to provide framework for explaining electromagnetic forces, nuclear forces, and also classifying subatomic particles.
So I assume it plays a really kind of key role then in physics and also maths to some extent.
I would assume so, yeah.
Yeah, because, I mean, it's in the Millennial Prize problems, so it must be really important.
Yes, I mean, this does seem to be based quite a bit in physics, but
Yeah.
I guess all the equations do make it related to maths.
Yeah. But I think some of the other ones as well, they're not all, like, specifically to do with maths. Like, quite a few of these problems
It's applied maths, I would say.
Yeah, they have quite a lot of application in other areas. So, that brings us neatly onto our next problem, which is P versus NP. So that's basically asking if a computer can verify the solution to a problem, can the computer then go on to find that solution?
So I think computer scientists don't believe that P can equal NP.
Yeah, so...
what is a P problem then?
So a P problem is basically a problem that can be solved and verified, but an NP problem can be verified, but it can't be solved.
Wait, so how can it be verified when it cannot be solved? So it doesn't have a solution?
I think it does have a solution. It's kind of like the example, so say like 5x equals 15, for example. An NP problem, it can, if you say, okay, x is equal to 3, it can put that into the function and see, okay, 5 times 3 equals 15. So that's the right answer.
Yeah.
But it can't do the reverse. So it can't do 15 divided by 5 gives 3, which is x. So it can't kind of work backwards from
Oh, okay. Oh, that does make sense, actually, yeah.
Yeah.
So again, actually, this does link pretty well into our latest video.
Yeah.
One of the more later ones that Greka made on cryptography. So do you want to go on about that?
Yeah, so if you watched our latest video, which if you haven't checked out, by the way, please do, because it's actually really interesting. So basically, if you don't know what cryptography is, it's kind of like, it's like ciphers, so encoding and decoding information, and it basically relies on the assumption that factoring the product of two large prime numbers is not P, so it can't be solved and verified. So that kind of links really well with our previous video. So if you want more information about that, please check that out. But I also think it kind of ties in really well with computer science. So
yeah, so again, like we were saying earlier, this is also like a pretty good like application problem into computer science instead of like physics, like the Yang and Mills one.
Definitely.
And yeah, so I guess we can go on to our next one now, which is the Hodge conjecture. And the Hodge conjecture basically questions if complex things can be built up from simpler ones.
Yeah, and we're not really sure if this is the case in 4D. So like we've got 2D and 3D, we've also got 4D.
Yes, like when water sprayed on you in a theatre or something.
Yeah.
For a bit more of an example.
But we're not really sure if that's the case or not. So that's kind of what the Hodge conjecture is asking.
So it's basically one important class of mathematical objects, which are called the projective algebraic varieties for information, and they're basically made up of pieces called Hodge cycles. And those Hodge cycles are again made up of smaller pieces called algebraic cycles.
Yeah, so I know that sounds really confusing, but you can think about it like, imagine seeing a Lego city and from far away it looks like it's working and everything's fine and looks like a city. But up close you can kind of see that it's made up of these smaller blocks. So that's kind of what the Hodge conjecture is all about. It's kind of asking, is that the case or is that not the case?
So it's like each object made up like smaller Lego blocks, if you link it back to the example.
In my opinion, that one's definitely one of the more confusing ones, because when I first was researching that, I was a bit unsure how that kind of ties into maths.
Yeah, I'm gonna be honest, I don't really fully see how it ties into maths, but I think when it comes to understanding what the question is, I think the whole Lego City thing really does help.
Yeah, definitely.
With the building blocks.
Yeah.
Because I wasn't sure what it was talking about when I first read it either.
Yeah, it's definitely one of the most confusing ones. But do you know what's supposedly even more challenging? The Birch and Swinnerton Dyer conjecture. Is that how you say it? I think.
I hope so. Birch and Swinnerton Dyer conjecture. Yeah, let's go with that. And this one is widely recognised as the most challenging problem in maths. And it basically describes the set of rational solutions to equation to finding an elliptic curve.
So if you don't know what elliptic curve is, it's basically, in simple terms, like a squiggly line.
It's basically a curve. When I searched this up, I saw that it's basically a curve defined by a certain type of a cubic equation with like two different variables, like a and b, x and y, all that stuff.
Yeah, so some things are infinite. So like your positive numbers, they keep going on and on and on. Like you can't really say where they end. And then, but some graphs, they'll have a finite number of solutions. So if you take like a quadratic graph, for example, x squared, it's only going to cross the axes like a certain number of times.
Yeah.
But I imagine with a graph like y equals sine x, like that's going to keep crossing the graph like
multiple
the
times.
axes.
Yeah. So is that like a simpler way to tell if elliptic equation has like a finite or like an infinite number of rational solutions?
Basically, yeah. I think that's kind of what it's about.
Is that basically what you have to try and solve?
I think so, yeah.
Oh, okay. So yeah, let's go into our next one then. So this one is the Navier-Stokes equation, and these are basically like a set of equations, and they relate to velocity, pressure, temperature, and the density of liquid. Now, the equations don't work for incompressible liquids,
but they do model all the fluids on Earth. So
yes.
They've got a lot of kind of, again, like we were saying earlier, they've got a lot of practical applications. So we can model the weather, we can model ocean currents, water flowing in a pipe, like airflow around the wings.
Yes, I think they seem really useful.
Definitely,
yeah. But the idea of this is to basically prove that either solutions, when it comes to the incompressible fluids, I cannot speak. Incompressible fluids exist, that they meet, like the solutions meet certain conditions, or that to prove that the solutions don't always exist, and the equation breaks down.
Yeah.
If that makes sense.
And these equations are non-linear. So what we mean by that is you can't use traditional linear methods to solve them.
Yeah, so like substitution and all that jazz.
Yeah. But I think these are really interesting because they kind of describe the physics of a lot of really interesting things. So like science and engineering. And I definitely think it would be really interesting to touch on these in some of our future videos and our future podcast episodes.
Yes, definitely.
Yeah.
So our last one of the 7 is the Riemann hypothesis, if I said that right. And it's basically, to put it in simple terms, is the secret to the pattern in prime numbers, hidden in the zeros in the zeta function. The zeta function is literally just like an equation sort of thing. So something like when you have f of x equals x plus 2 or something, but obviously more complicated. And it's basically showing that the prime numbers, generally in a number line, prime numbers aren't distributed evenly.
Yeah, because you start with them being really kind of close together and then they'll start spacing out a bit more. So, yeah.
But I think he's German, I'm not 100% sure, but a scientist called Riemann, he discovered that the numbers are distributed very similarly to the zeta function that I mentioned before.
Yeah.
And
all the zeros of this function, they lie on a straight line, and we call that line the critical line.
Yes, I think the line is somewhere between 0 when x is 0 to 1.
Yes. Yeah, you're right.
Yes.
Yeah. And I think a lot of mathematicians actually believe that this hypothesis is true. So because all the calculations that they've done so far, you haven't got any misbehaving zeros that don't really lie in that critical line.
Yeah.
But I mean, there's literally an infinite number of these zeros to check. So, a computer calculation can't verify all of that, and it can't say for certain whether it is true. And that ties in really nicely with our P versus NP problems.
Yes, yeah. I think it's kind of cool how, like, sometimes these problems do kind of link with each other.
Yeah.
And I think, honestly, most of these are actually applied maths. It's not just,
definitely,
here's an equation, solve it. It's, like, related to computer science, physics, and also, like, the Navier-Stokes one you can use it in real life too, which is pretty cool.
And I think this really, in class, there's a lot of people that's like, what's the point of doing maths? But I think these are kind of really nice, interesting examples of how maths is actually really useful.
Yeah, I think this is definitely, like, real life application, like you said.
Yeah.
Which honestly just makes them more interesting.
Mm-hmm. They are confusing though, I'll give them that.
Yeah, I'm going to be honest, I'm not sure if
It's a lot to digest.
Yeah. Quite a lot of information.
But, I mean, if you've got any time,
why not give it a go?
Yeah, I mean, you might get somewhere. You might be the next person to win that $1 million prize.
We can hope.
Or if that doesn't float your boat, you can just have a go at researching some of these and see if you can find anything else.
So thank you for listening, and we hope we haven't bored you to death with all the information. And please leave us a rating and on Spotify, Apple Podcasts, whatever.
If you're watching this on YouTube, be sure to like, share, and subscribe, because we've got more podcast episodes coming for you, and plus also we've got a whole range of cool experiments.
Yes. We've got some plants, some boats.
Yeah, we've really planned it all for 2024.
And stay tuned for our next podcast episode too.
Yeah. Thanks, guys.
Thank you.